this is the mask that we have, and we multiply them. This is I and this K is your kernel, and we perform the convolution. So pixel by pixel matching, we can see these two. This is the symbol for convolution. So if you are unclear on the concept of convolution, I hope that you would have studied them in signals and systems or digital signal processing course. So kindly revisit that, and if you're still unclear, we can discuss this in the next lecture. So these two matching, and then only this one is matching, and we have 1 plus 1 plus 1, that is equal to 3. So we sum up all the matching pixels, and the answer comes out to be 3 for this convolution operation. And in convolution, we know that we are basically sliding our window or kernel on the image and getting our value of the summation of those values, multiply pixel by pixel, and then sum them up at the end. So if this is our kernel, or we can say this is the mask, this is your mask, and we apply this on this section of our image. This is 3x3 kernel. Kij and I will be applied to these values x and y. We can take I and j. Okay, so we apply the kernel over here. So multiply -1 by 0. Okay, this and this, then this part again 0, this will also become 0, this will also become 0, this will become 0, and this will become 0. Again this part becomes 0, this part becomes 0. However, if we multiply these two terms, we get -1 to 1. This is -1. So the output of applying this kernel onto this part of the image, we get this at the center. This is how we apply the kernel onto the image. In the next step, we slide the window, the kernel down 1 pixel, and again calculate the convolution. So this becomes 0, 0, 0, 0. This becomes -1. This becomes 0 again. This becomes -1, and this becomes 0. So the sum total is -1 plus -1. It is -2, and we place the value at the center of the so this is now value for 1 pixel slide, and then we calculate like this. The next one we get is 1, and similarly we slide the image first downwards, then this, and we get these values. After obtaining these values, we are left with the outermost part. So if we want to get a value over here, the center, Then we will place, for calculating at this part, we will consider this to be multiplied by this, and the rest of the values that we will consider is 1 to the left and 3. So considering these 3, let's suppose we have 0, then we have 0, we are only considering this part, then we have 0. So this is the calculation at this point. And what about the calculation for the next point? How we are going to get, so now we have calculated this. What about this? So if this is the center, okay, here center, then we will consider all of them. They're all 0, so obviously we will get a 0 here. Okay, now what about this part? Only one value is -1, so we place a -1. So similarly we go down, and then we can get for all those on the border. So this is how your convolution is estimated, and we have this map that has extracted features from the original image, from this image, using convolution. Kernel. Okay, we used the kernel or to find the features within this image, and once we have found those features, what we can do is we can also use a threshold. So we only consider the non-negative values, and if we apply this threshold, we will get here. So how do we get here? Let's go here. So in this one we only have my non-negative value here, greater than 0 only. So let's see if, yeah, so we are applying the threshold. Now we will get 3. Let's look here. So we can get the values using a threshold, and we have most of the values now you can see are 0 in this feature extraction, and only the important features are kept. So this part will extract only the important features within your image, and the rest will become 0. So look at the original image. This was your original image, and we have extracted the most important features using convolutional neural networks, convolutional kernel. And what about a 3D image, RGB image? So no big deal. We have one for the red, one for the blue, one for the green, and similarly we will have different kernels. We will have 3 versions of the kernels, and each pixel value will be the sum of the values applying the kernels. This will give us one value, this will give us another value, and the third kernel will give us another value, and total sum for one position will come out to be 1, because essentially our image is a combination of R, G and B values, right? So the output is 1 value. Applying the 3D kernel also, we will get value like this. The feature map extracted from the 3D image will again be a single value for each calculation. For each RGB, we will get a single value. Okay, so an example of kernel. For example, this is our kernel that has been designed to extract the horizontal line within our image, And if we apply like this, then we go 1 pixel down, then 1 pixel down, like this. If we apply to this image, it has extracted the horizontal lines within your image. So what feature are we extracting from here? We are extracting horizontal line, only the horizontal line within the image, right? So feature extraction. We are trying to extract the features from the image, and we can do the subsampling, or we can call it the pooling, from m by m pixels into 1 pixel. So we can use different kind of pooling mechanisms: max pooling, average pooling, or LP pooling. There are different ways. So for example, this is your feature map after the threshold. So first we applied the convolutional kernel, then we applied the threshold to get this feature map. Okay, we obtained the feature map, and now we can reduce the dimension of this feature map using or pooling, or we can do the subsampling, and m by m pixels, 8 by 8 pixels can be reduced to 4 cross 4 pixels. So m by m pixel can be replaced by 1 pixel. So what does the max pooling does? For example, if we are taking the max pooling concept, we consider for example, the 2 by 2 pixels, and then find the maximum value and replace it in our subsampled feature map. For the next, we are not going moving pixel by pixel sliding, rather we are moving pooling filter size 2 by 2 pixel, and we are jumping to the next. So we have 2 by 2, we get this max pooling gives us 1, this one gives us 1, and this one has the max value 3. So this is our max pooling. If we apply the average pooling, so the average pooling concept would be the same. All that you do is, the difference is that you're taking the averaging. So the feature map is further subsampled to extract the most important features and reducing the size dimensions of our feature maps. So we have a subsampled representation. So what are the advantages of pooling? It reduces the number of parameters, and it generates more robust feature maps, which we can say which are shift invariant. And what do we mean by shift invariant? So for example, we have an original image. So this is our original image, right? This was our original image. For example, value of 1. This is our original image. And then we have a shifted version, 1 pixel shift. So all the values are shifted by 1 pixel. So these two ones that we have here, they have now shifted one place vertically downwards, and you can see that if now we apply the max pooling concept, this is the feature map that we got before, and with the shifted version we get this output, and we can see the similarities between these two feature maps. So these green highlighted ones, they are common between the two feature maps that are obtained, one with the shifted image and one with the original image. And now we will have more non-zero values will be matched between the two versions. So we can say that to an extent, or pooling is shift invariant if the shift is not too drastic. That is to be remembered. Not too drastic or not too much shift. So, or we can still be able to extract the samples from our feature maps using the pooling concept for subsampling. So we were discussing at the very beginning that we are trying to extract the feature maps for a translation or shifted version, rotated or squirrel version. So, or when we are extracting the features, and if we have a scaled or shifted version, we could still be able to use some of the methods in convolutional neural networks to extract the local feature maps from the images. So now we are here. The process is that you give an input image. This is a grayscale image with 1 and 0s. We apply the convolution kernel, then you apply the thresholding, then you do the max pooling to finally obtain your subsampled feature maps. Feature map, again, we can consider it as an image, and we can extract many different feature maps from the image. And if we, so here we only got one feature map,